Hi everyone, and welcome to Eric's Electronics Workbench. In this video, we'll be taking a closer look at this vintage Cornell-Dubilier model BF-50 capacitor analyzer. So let's get started and see what it takes to bring it back to life. So this Cornell-Dubilier model BF-50 capacitor analyzer dates from probably the late 30s into the 40s. There are some patent dates on here from May 6th of 1930 and September 15th of 1931. The manual that I found online has a date from 1939 in it, and there's also a mention of tube shortages from the war, meaning World War II. So, it dates it around that time period. Now, the unit looks like it's in original unrestored condition. We'll open it up and take a closer look inside and see, exactly what's going on inside, if there's anything that needs to be done. But ultimately, we'd like to power it up and see if we can bring it back to life. So we'll check that out shortly. Now, the wood case, has some scuffs on it, but nothing too serious. Just, what you would expect, typical condition for an instrument of this age. The front panel looks, very clean and in really good condition. Now, the lid or the top cover hinges on the back. One of the hinges is missing a part of the hinge, so I have the cover set over here to the side. It pivots and it will close. It'll latch closed on the front, but for now I just set it off to the side. You can see the cord is actually in pretty good shape. It still has a little bit of able to be flexed around a little bit. It doesn't feel too stiff and dry, so we'll check for any short circuits, but it may be good enough to test with this original cord. Amazing, it appears to be the original cord on there. I've seen those cords of that age, be just as stiff as a board. Now these test leads, they're not anything special. They're just the banana jacks on the end. They're pretty stiff. The installation's not too good, so we won't use those. This end here, this is probably like a vinyl or something that's just hard as a brick there. So we'll set those aside for now. The test jacks here, regular banana jacks, will plug into there. So modern test leads are perfectly fine to use on that. And the front, or the top cover rather, has the instructions printed inside, which is pretty cool, and it's in excellent original condition. The paper is not deteriorated or anything, very legible. So the next thing I'll do is get this taken out of the wood case, and it looks like it's just a matter of taking these screws out of the perimeter around the front panel, and then we'll see what happens. So get this over here and take these out. Screw in the corner right there to come out. Looks like those are all free. Here it's got a little bit of weight on the back of that chassis in there. There we go, it came free. It was catching on, looks like some switches or wires or something down there at the bottom edge, and sort of a lip in here, and this was catching in there, but that looks like that's free. Get that out of the way. So set this over here. I'm going to turn this upside down. I don't think that'll hurt anything on the front. It'll just rest on the there like that. Interesting. So it looks pretty clean inside. Pretty good condition in there. Get the camera, we'll zoom in here and take a closer look and see what's going on inside here. So it looks like all original wiring. You can see how they have the wire loomed, and it has the little cord or the thread that goes along there to loom that wire. So that looks like it's all original. Don't see any components that look overheated or damage just at first glance across here. Now, we want to try and power this up. And a full restoration on this, you'd certainly want to be getting rid of these old wax capacitors. We'll take a closer look at some of these resistors and see if things are within range, within tolerance. These early resistors with the rounded ends on them are prone to drifting. They can absorb moisture and definitely drift and wander around in tolerance. If you measure a couple of them and they look good, then likely the rest of them will be okay. If you measure one or two and they're way off, then likely all of them are off. And the reason for that is if it's stored in a very damp location, then they're all going to be affected basically the same way. So if it was in more of a dry location, then likely they've lasted a little bit better, and they're probably not going to be right on value, but they'll probably be pretty close. So we'll check and see exactly the condition of those resistors. These power resistors like this, they are pretty stable. Potentiometers, no issues with those. They're a wire wound type potentiometer. They're stable, they don't drift. Now these capacitors up here, these blue capacitors, those look like electrolytics, and yeah, now those look like they have leaked. If I tip this up here, bring this up maybe a little bit closer like that, the camera, I think you can see this one over here definitely looks like there's a kind of a white stain or something going on in there. So no surprise on those. They're probably completely dried up or electrically and physically leaking. I don't see anything running out of them, but it looks like something has kind of come out there. So those are definitely going to need to be changed. Yeah, the other end doesn't look too bad. I'm not sure. Might try and power it up with those in there, just on a low voltage to see if the transformer and things work okay. If the tubes light up, would be a good thing to test. But before we really bring it up to any full voltage levels, these would need to be changed out. They're definitely going to be faulty. Take a look at the back here. So it looks like some transformers down inside. See the tube over here that comes through the front panel, and there's the eye tube on this side. Just goes into the sockets there. So it looks pretty clean. Looks really original condition, which is really nice to see. So let's take a couple measurements on here and see for the resistance. Let's start with the cord, and I'll move this over a little bit like this. The meter here, see if we can get that into the shot at the same time. So we want to look for any serious short circuits. We're not going to want to put any voltage, any power to the unit if there's a dead short, say on a transformer or something like that. So what I will do first of all, the power, I believe the power switch, this white button over here was the on off, so go like that. I think that should put it in the on position. So with the ohm meter, we'll start by going across the plug over here like so. So you can see the ohm meter is reading, looks like right about 20, 19, settles right in there, 19 to 20 ohms. So that's reasonable. That's the primary winding on the power transformer. So no short circuits in the cord, so that's a good thing to see. Another test here. Let's check from the cord over to the chassis just to make sure we don't have anything going on there. Looks good. Open circuit. And looks like that's an open circuit, so that's good. So no short circuits between the line cord and the chassis. So if you're following along at home and working on one of these units, please know that you do so at your own risk. These units are very dangerous. There's high voltage everywhere inside when the unit is powered up, and once the unit is turned off, high voltage can remain on these capacitors for long periods of time. So very dangerous. Please refrain from working on something like this unless you fully understand the dangers involved. So again, you do so at your own risk. So let's take some readings on several resistors and see if the values look like they're in spec or not. So we'll start over here with this resistor. This is a red, green, orange. So that's a 25K resistor, 25,000 ohm. So I think you can see, let me put this maybe like so. I think there's a little bit of a glare on that screen. Yeah, there, that shows up okay. So again, this resistor right here. So we have 27.25 K ohm. So not too bad for a 25K ohm resistor, 27K. You know, these tube circuits are pretty forgiving on a lot of the values. If they shift a little bit around, you know, that's not drifted, you know, way off. So something like that is perfectly fine, you know, especially for initial testing. No issues with that. Let's take a look at this resistor back here. So it's a red, black, red. That's a 2K ohm resistor, 2,000 ohm. So if we come in like so, yeah, that one's right on, 2.014. So that's looking good. So two resistors there, those are looking very good. Let's take a look at this resistor back here. This is a little bit faded, but it looks like a green, black, yellow. So green, black, yellow should be a 500K resistor. That's half meg ohm. It actually looks like this is probably the same over here. This actually looks a little bit, it might be just be a coating or something on there. It looks a little bit crusty. It doesn't look too, I don't think it's overheated or anything, but it's definitely faded on there. It just probably just the age on it. But I think that looks like a green on there. Definitely black band and then yellow. So looks like both of those are the same. So let's see what they check out as. This comes over here and this comes over here. Yeah, that's 0.589, yep, 0.59 megs, 0.6. It's changing a little bit. There may be a capacitor in that circuit, but 0.6 meg ohms, which is 600K. So no problems there. If you have a capacitor across the resistor in the circuit, it can cause the value to kind of keep creeping up as the capacitor charges. The ohm meter's, you know, putting voltage across that resistor for the test, and a capacitor will affect it. So that other resistor, it looks a little bit rough on the outside there, but it checks out at 0.489 megs. So right in spec, no problems. Just shy of half K, not half K, excuse me, 500 K ohms, half meg ohm. So that's several resistors are all looking very good in the circuit there. No issues at all. So that's good to see. So the next step is to apply some AC, and we want to see if the transformer is functioning okay, and also you know, if the tubes turn on and start to produce a little bit of DC. Now these capacitors, we'll definitely need to be changing these out before we put full voltage to the unit, but you know, I want to see if the transformer is functioning and just see if a little bit of activity occurs in the circuit. So we'll do that next. Now to power this up safely, and when you're working on any type of equipment like this, you want to use an isolation transformer, and also current limit the input through an incandescent bulb. If there is a short circuit or an overload, the bulb will glow very bright, and if the unit is operating correctly, the bulb will have a very dim glow. Also, these capacitors in here, this hasn't been powered up for possibly many years, so once this is, if we do the repair, if this looks like there's going to be some activity, we'll change these out. Then we'll let the unit sit at a very low voltage with that current limiting in place for, say, half hour or so, and just let the capacitors form, just let everything sit for a little bit with that low voltage on it. So we'll get to that second. The first thing to do is just some low voltage, just to see if there's some activity in the circuit. Now, this uses a 12A7 tube, and that 12A7 provides the DC, the rectification. It has a half-wave rectifier, so there's a diode in that tube, and there's also a pentode. The pentode is part of the measuring circuitry in here. but the diode is in the power supply. You can actually see between these capacitors, this capacitor right here has this lead that has a black sort of insulation on it, and it comes over here and it goes right to the tube. So that's very likely the B+ line, the main high voltage, and it's a filter capacitor. Okay, I'm ready to bring up the voltage slowly, but before I do so, I wanted to check and make sure that there's not a short circuit or any low resistance on the rectifier section of that 12A7 tube and this filter capacitor. We know the capacitor is likely in poor condition, and I just wanted to make sure that there was no short circuits or anything, with a too low of a resistance that would cause a problem. You can see it's 0.624 megohms or 624 k ohm. So that's perfectly fine and shouldn't pose any issues. Just to do a quick test and see if we have some activity and a little bit of voltage showing that the transformer and that the rectifier tube is functioning. We'll be looking for a DC voltage in that circuit, actually on the same points that this is connected to. I'm just going to change this over to the DC voltage mode. So we'll actually be looking for some DC voltage there to see that the rectifier tube is functioning correctly. So I'm ready to bring the voltage up slowly. Again, it's through an isolation transformer, and it's current limited with the incandescent lamp in series with the power cord, and the voltage is brought up slowly using a variac. Okay, the AC voltage is turned on, and I'll begin increasing the variac to bring up the voltage slowly. The incandescent bulb is remaining dim, so that's a good sign. So, of course, the tube may be defective, the filament could be burned out. We don't know if that's even functioning yet, so we'll find out here. Now, it does look like something is starting to creep up there. Of course, it's a fraction of a volt, very small. No, looks like there's a little bit of activity there. So that's a good sign. A tenth of a volt is all, it's not much, but it's trying to do something there. Yeah, look at that. It's coming up. I've got half a volt there. 1 volt. Of course, there's just a very low voltage going into the unit right now, so it takes some time for the tubes to warm up and come into emission, and we're not going to expect to see much voltage. Likely those capacitors are defective and not even doing much anyways, so it's a half-wave rectifier, and if that capacitor isn't doing much, assuming that it's probably all dried up, then the voltage would stay very low anyways. You would just be getting basically a pulsating DC voltage in that circuit rather than being filtered, and once that capacitor is filtering, the voltage level would rise up. So it does look like it's functioning as far as the transformer, and the tube clearly is working, the rectifier tube, that 12A7. We've got some DC voltage in that circuit. Now this is the B+, and it's probably likely upwards of 400 or 500 volts, maybe it's closer to 600 volts, something like that. I'm not sure exactly what the value should be, but it's many hundreds of volts. I think those capacitors were rated 500 volts. It may have been 600 volt caps. I'll have to look again. But it's a long ways off from that voltage, but it clearly is able to function. It doesn't look like anything is shorted out. The incandescent bulb for the current limiting is remaining very dim. So that's all a good sign. So at this point, I will turn the AC power off, and you can see the voltage just falls away. And I'm going to get these capacitors replaced, and then we'll try and power up the unit and see if that voltage can come up to the full rated B+ voltage. Again, should be in the many hundreds of volts. And we'll see if the unit comes to life and has some activity, and particularly take a look at the I tube and see if there's some activity on that tube as well. So I'll be back with those capacitors installed. Okay, I have the replacement electrolytic capacitors installed. You can see them here. Now the original capacitors were rated 8 microfarads at 500 volts DC, and these replacements are 8 microfarads at 600 volts DC. So when replacing capacitors, you always want to use an equal or higher voltage rating. And you can see the original capacitors. They're of course made by Cornell-Dubilier. They manufactured the tester, but also all the capacitors in here. And you can see they called these the Beaver, this is going to light a little bit there, the Beaver Dry Etched Foil Electrolytic Capacitor, the BR-850. But these are completely dried up. You can see it looks like it's been leaking on the end there, and just no life left to these whatsoever. And in fact, if I move this up here, put them on the tester, and do this. Let me zoom in the camera a little bit here. So if we put the tester across there, I mean, you can see the tester actually doesn't even recognize the capacitor. It's completely open. If you force it to run a test, it just comes back and says open circuit, low capacitance, so nothing there. And this capacitor here, it does recognize it's there, but then it says open circuit, low capacitance. So, but not surprising, electrolytic capacitors of that age are not going to be good. So with those replaced, we're ready to power up the unit, and we'll do so very slowly. I'll be using that current limiting through the incandescent bulb and the isolation transformer, and of course the variac to bring the AC voltage up slowly. Back the camera out a little bit here so you can watch the voltmeter. Move this over. Position that. So what I'll be doing is monitoring the DC voltage that's on the rectifier tube, and that comes to this capacitor right here. So we'll be looking for a positive voltage at this terminal and a negative voltage over here at this junction. Now, incidentally, when I was replacing these capacitors, this solder connection right here was broken, and they had a J hook on the end, and it was in place, but the solder was actually broken. It may have been broken for many years, hard to say, but the original capacitor, had a little bit of weight in there, may have been just bumping around over the years and just broke that solder connection. So that would be affecting how the unit could function. So it was good to get that taken care of. The connection down here where the line cord comes in, this solder didn't look too good. It looked original. I don't think anyone had messed with it, but it didn't look very good. It didn't look like it had, the solder hadn't flown around or adhered to the terminal on this tag board. So I cleaned that up a little bit, and this resistor right here comes over to a ground connection. That ground connection solder, rather, where this resistor lead comes in right here, was loose. It was a cold solder connection, and was just sort of bumping around within that solder. So when I saw those two connections not looking too good, I looked over the rest of the wiring in here, and actually did not see any other issues. All the other solders looked good, but it was good to get those taken care of, because that certainly would affect how the unit would perform, or may keep it from working at all. So I didn't look in the circuit to see exactly where those solder connections were, but at any rate, they needed to be taken care of. So those are fixed up, and we'll go ahead and power up the unit. I'll get the voltmeter connected here so we can monitor the voltage. Okay, the voltmeter is connected, and it's across the main filter capacitor, so we'll be measuring the voltage as I bring the AC up slowly. And once I bring the voltage up to a low level, I'll let the unit sit for about a half an hour at that low voltage, and watch for any signs of problems or any troubles, and then from there we'll increase the voltage some more. So at this point we'll turn on the isolated supply. And it is now on. It's on at a low level. The incandescent bulb is glowing extremely dimly. Hardly see it at all, which is a good sign. So hopefully we see some increase in that DC voltage. Of course, the tubes have to come into emission for that rectifier tube to begin conducting, and with the AC voltage very low, that heater is going to be very slow to warm up. Of course, the rectifier tube filament needs to come into emission before that tube will begin to conduct, and it looks like some slight activity there, very, very small voltage, but it is starting to increase. Yeah, it looks like we have some activity there. Now this voltage should be in the hundreds of volts once the unit is up and running, but we won't let it get that high at this point. So there's 76 volts, 75 volts. Turn the AC down just a little bit. 70 volts. So that looks pretty good there. I'm going to let that sit now for about a half an hour at that 70 volt level and just monitor that. Make sure that there's no issues, and then we'll increase the voltage some more. Okay, the capacitor tester has been on now for about a half an hour, and the DC voltage has stabilized around 83.5 volts, 84 volts, right in that range. So now I'm going to increase the AC voltage upwards towards the normal 120 volts AC that the unit would normally operate at. In the half hour that it's been on, there's been no issues. The voltage looked good, it's been stable, and nothing has become warm or overheated, no issues like that. So everything has been looking very good up to this point. So now I'm going to begin increasing the voltage some more. So now the voltage is quickly rising, which is a good sign. Still increasing the AC voltage. So that's looking very good. Still increasing the AC voltage. About 100 volts going into the unit right now. 100 volts AC. Still increasing. And there's 120 volts AC input. So that's looking very good. So 462 volts DC. Now if we turn this to the AC position, that's the ripple voltage, and 5.8 volts. It's not bad. There's no inductor, and this is just a half-wave rectifier, not a full-wave rectifier, so you do have that pulsating DC that capacitor needs to smooth out. So in a circuit like this, you will typically get a fair amount of ripple, and so that 5 volts AC is typical, but very tolerable. No signs of issues there. So again, the DC voltage holding nice at 461, right around there, so looks good. Okay, the tester was powered up successfully for over an hour with no issues. So I repositioned it as you see it here so that we can try out the tester and see how well it functions. Now I'll be powering up the tester off the isolation transformer, but I've replaced the incandescent bulb that was in series for current limiting with a 1/4 amp fuse. The 1/4 amp fuse at 120 volts provides 30 watts. The tester is rated 115 volts at 25 watts. So the fuse will provide the safety that we need should there be a short circuit or an overload inside the tester. That fuse would go away. Now, the tester has two basic functions. It has a leakage function and the capacity function. So we'll start with the leakage function first. Now, the in and out references on the switches refer to the switch being in or down and out is up. So you can see the various combinations that you would select. And for the different tests, at any time you would have no more than 2 of these switches in the in position. The switches down here control, of course, power and the various capacitance ranges when doing the capacity test, and the voltage ranges on the electrolytic leakage test, and those voltage ranges are the voltages applied to the capacitor under test. So starting over here, the top button is in the leakage position, which is in. We'll start with the paper and mica test, so that's out or up. And the voltage control is used in the leakage test. However, it's not used in the paper mica test, but we'll leave it in the up position or out position. The sensitivity and voltage control on this button are referring to this control right here. And on the leakage test, when you're using the electrolytic mode, these ranges 0 to 100, 100 to 200, 200 to 300, 300 to 400, and then 400 to 600. The range is controlled by this voltage adjustment. So these are actually 10 volt steps, 10, 20, 30, and so on. So for example, if you were to select the 0 to 100 and position this at the 40, that would actually, or the 40 position here, you would actually have 40 volts on the output. If this was selected, it would be 140, 240, and so on. The sensitivity control is related to the capacity test and how sensitive the tester is during that test, and we'll get to that shortly. Of course, over here on the test jacks, the capacitor that you're testing is connected between the plus and the minus. Very important to watch because the polarity on an electrolytic capacitor, the capacitor's positive must be connected to this plus up here. And of course the negative. A paper and mica capacitor doesn't have polarity, so it can connect either direction. And we'll just be plugging test leads into these jacks that have clips on the end. The ground connection just connects to chassis ground. We won't be making any connection to that. The manual does mention a ground connection if you need very accurate measurements, and I suspect that may have to do with this eye tube. If it's noisy or not giving a correct reading, something like that going on, then a ground connection could solve that problem. But for now, we'll leave the ground connection disconnected. Now, on the eye tube, you can see the leakage scale that's up here with the red band in the middle. So on an eye tube, you have what's called a target, which is sort of that round dish-looking shape in there. And that target fluoresces or glows sort of a green color. And on the top, there's a segment or a wedge shape that opens and closes. And these are often called a magic eye tube or a magic eye. So if the capacitor under test is very leaky, the eye will close together, and that's what this red area is indicating. So if the wedge shape is equal or smaller than this wedge shape right here with the red, then that would indicate a problem. And what you're looking for during the leakage test is really a wide open wedge shape in that green color, and that'll be very obvious once it's powered up. Of course, the capacitors that I have to try out the test are known good capacitors, but we'll make them leaky by putting a resistance across the capacitor, which would simulate a leaky capacitor, so we'll be able to see how this tester responds and what actually happens on the eye tube. So before we connect a capacitor to the tester, we want to make sure that these voltage ranges are correct and accurate, or at least within reason. On a tester of this age, 100 to 200, I don't think the voltage will be spot on at 100 to 200, but certainly it should be within that range as this control is adjusted. You wouldn't want to see, for example, 400 volts being applied over here when you're in the 100 to 200 range. A high voltage over here could damage a capacitor if you weren't expecting that kind of voltage. So again, these voltages are related to the leakage test and the electrolytic mode. So we'll actually do that test first just to see if the circuitry is working correctly on those ranges. So I'll reposition the tester and the meter and power it up, and we'll see if the output voltage is correct. Okay, I have the tester positioned with the digital multimeter connected to the test jacks, and we'll see if the voltage ranges look correct for the leakage test. Over here we have it in the leakage mode and the electrolytic mode, and we'll vary this adjustment and see how well that corresponds to these ranges. Again, this 400 to 600 range, the tester does not actually put out up to 600 volts. I believe it stops around 450 volts, so we wouldn't expect this to go all the way to 600. That is mentioned in the manual about the limit stopping around 450 volts and not going to 600 volts. All right, I'll turn the tester on and we'll see if the voltage ranges look like they're working correctly. So it looks like the voltage is increasing already on the output jacks. I have this in the 0 to 100 range, and that looks very reasonable, 110. Now there's no capacitor, of course, connected on the test jacks, just the meter, and the meter has a very high input resistance. So that could cause some variation in these readings because there's no current draw as a capacitor would charge. So I imagine that could affect the readings as well. But it's good to see that 0 to 100 is holding 108, so very reasonable. So 100 to 200, we have 203 volts on the output. You can see the tube over here, the I-tube is glowing green, so that's a good sign. I'll turn the overhead light off here and we can see that on the camera a little better. 200 to 300, looks like 301, that looks very good. 300 to 400 range, 411, so again, very good. And the 400 to 600, looks like 462, 463. So very reasonable. Again, the manual mentions that this does not go to 600 volts. It's interesting that they printed 600 on there, but it actually doesn't go to that range. But 463 volts, which is about, I believe, the B+ maximum. So those values are looking very good. So I'll reposition the tester now and connect a capacitor across the test jacks, and we'll do a leakage test. Okay, I have the tester connected to a capacitor, and I've turned off some of the overhead lights so that you can see this I-tube glowing, and that's a very good sign that that's turned on. And you can see the wedge or segment in the top is open right now, but we'll watch for activity on that during the leakage test. Now this capacitor is known to be good, but we'll make it leaky and see how this responds for a capacitor that would be leaky, and we can do that by connecting a resistance across that capacitor. So this is in the paper and mica setting in the leakage mode. And in that position of leakage and paper mica, only this C5 button, which said 400 to 600 volts with C5, you press this button to run the test. However, it does not put 400 to 600 volts, anything in that range, out to these test jacks. We'll take a reading and see what actual voltage is on these terminals during the test. I'm not sure what it is. I selected a capacitor with a 600 volt rating because I knew that was well above what this tester could supply. With using testers like this, you want to be very careful of the voltage that's applied to the capacitor, because certainly you could damage a capacitor if it was not rated appropriately, and a capacitor that you might find in a modern circuit that was, say, 25 volts or something like that could easily be damaged on a tester like this, because it just was simply not made to test low voltage capacitors. This is really for capacitors in the 200, 300, 400, 500 volt ranges that were very typical back in the day when this was made. So before I run the test, I will zoom the camera in a little bit closer, like so. So you can see that I-tube. This up a little bit here. Yeah. So we'll run the test, press this button. So you can see the I-tube opened and is remaining open, so that's a very good sign. Now again, this capacitor is known to not be leaky, but we'll put a resistance across it and see how this tube would react, or how the tester rather would react, and how the I-tube would indicate a very leaky component. But running the test one more time. Again, this is the press to discharge. Discharges the capacitor. You can see the eye tube close down, which would indicate current flowing into that capacitor since we just discharged it. And now you can see the eye tube opening. It's a very wide opening segment or wedge shape, which is very good. So it appears that this tester is functioning correctly for a leakage test in the paper and mica mode. We'll check out the electrolytic mode in just a little bit. Let me zoom back out again. And I will bring in the meter over here, like so. Let me turn on the lights here. And we'll take a reading across these terminals and see exactly what voltage this is applying to that capacitor during the test. So it jumped up fairly high and now it's dropping. Now this meter is acting like a leakage current basically, even though it has many megohms of input resistance. You can see the voltage drop down, and yeah, the eye tube is closed, so it's able to detect the current that the meter is drawing as it thinks is a leakage current. So that's a very good sign. It's very sensitive and is able to detect that. But you can see the meter is indicating 127 volts DC. So again, you would not want to use a capacitor that was rated, say 50 volts even, or 25 volts. It could be damaged. I'm going to turn the light back off and you can see that eye tube and how it's functioning. So if you see the eye tube, let me move these leads here a little bit. So the eye tube is completely closed right now, or very nearly closed, and now it's opening again. And that is normal, that this tester will, they say in the instruction manual, flash the eye tube, but you can see now how it just closed again. And that repeating opening and closing of that segment is normal, and how rapid that occurs tells you how leaky the capacitor is. So there's actually a formula given in the tech manual about counting how often that opens and closes, and that can be used to figure out what the resistance is in many megohms. So that's a pretty cool feature that that is calibrated and can actually be used to figure out the resistance value of the capacitor. Now this is acting like a leaky capacitor simply because of the voltmeter and its current draw, because the meter has many megohms, but that does cause a current draw and basically discharges that capacitor. So you can see it's sitting here, that eye tube is opening and closing, and when this was removed, the eye tube opens, and now it just remains open because, of course, that capacitor is a very good quality capacitor and has very, very low leakage current on its own. So that's looking very good. What I'll do now is put a resistance across that capacitor and make it look like a very, very leaky capacitor, something that was really would be a defective capacitor by today's standards. I'll put a 100 k ohm resistor across that capacitor, and we'll see what effect that has. Okay, I have a 100 k ohm resistor clipped across the capacitor, so that simulates a very leaky capacitor because the current will flow through that resistor and would be acting or simulating like what a leakage current would be internal in the capacitor. So the eye tube, you can see here, is glowing, and the wedge shape or segment is open on the top. And we'll start the test like so. So you can see it quickly closes, and it looks like it's remaining closed, which is correct. And there it popped open and then closed very quickly. And you can see now that's beginning to repeat. So again, when that eye closes together, that shows very high leakage current, and then the frequency of how often that opens and closes, or again, the manual refers to that as the eye flashing. You can use that to determine what the resistance would be. But you can see that the capacitor on its own, a very good quality capacitor with very, very low leakage current, that eye just remained open. So ideally, that's what you would want to see when using this tester, is that the eye does not do this repeating flash. And you can see that's happening fairly often there. So a capacitor on its own testing that way would be a very, very leaky capacitor. So the tester is functioning very well so far. So the next step is to check out an electrolytic capacitor, and we'll look at using these voltage ranges down here. So let me get the tester repositioned with an electrolytic capacitor. Okay, the tester is now connected to a 300 volt 3 microfarad electrolytic capacitor. And again, with an electrolytic capacitor, you want to watch that the positive is connected to the positive test jack over here. The polarity is very important. You can see over here it's in the leakage mode, and now we're in the electrolytic mode, and this voltage control is turned to the maximum, so that on each of these ranges it would be applying either 100, 200, 300, and so on volts. This is a 300 volt capacitor, so I'll select the 100 to 200 range just to start with, and we'll see how it functions on that voltage range. You can select lower ranges, but really to check the capacitor in what you would consider a real world condition, you want to apply the voltage that approaches its rated maximum. If you apply a very, very low voltage, it would perhaps appear that the capacitor is okay and has low leakage current, but you're just simply not applying enough voltage to correctly test the capacitor. So again, you want to apply near its maximum voltage. And again, I'll connect the multimeter to these test jacks, and we'll see what the voltage is during this test, and see how accurate it is and how it compares to these ranges down here with an actual capacitor connected. So to start with, again, electrolytic mode and electrolytic capacitor, but in the leakage mode. It's in press to discharge right now. The tester is completely turned on, functioning, and we will come over here to the 100, 200, watching the eye tube. In fact, I'll zoom in so you can see a little bit closer, like that. So the 100 to 200 position, and you can see that the eye tube is wide open, so that's very good. That shows that there's really no leakage current, or very, very low leakage current. So I will take the meter and let me zoom back out here. Let's see what voltage is actually on those test jacks. So right now this is in the 100 to 200 position, and we see 123 volts. If we turn this down, so it really does fall away quite a bit, down to 50. Turning this back up, slowly increases. So that capacitor does look like it changes those values, where before with nothing connected this came up to 200 volts when this was at the 10 position over here. Okay, I have the tester configured for the capacity test. We're using that same 3 microfarad capacitor, and the switches have been set for capacity, so the top switch is out or up. This is set for electrolytic, which is in, and this is in, which is sensitivity control, which I have at about mid-scale. Now, for this test, this is rotated, and the actual value of the capacitor is read, where this line, of course, corresponds to the different values of capacitance. The range on this meter is from 0.00001 microfarad, which is also equal to 10 picofarad or 0.01 nanofarads. and then a maximum of 240 microfarads. So a very usable range, a very nice range that they built into this tester. This being a 3 microfarad capacitor, we can see that this second scale starts at 0.2, then goes to 2 and to 4. So of course right in this range here would be 3. And that is the C2 scale, or the second scale. So I'll go ahead and press that now. So the eye tube, let me zoom back in so you can see a little bit closer, like so. So the eye tube is open, and what we want to see is a balance in the bridge circuit, and I'll explain in a little bit about how the bridge circuit actually functions and what that is, and we'll take a look at the schematic. But rotating this control, we want to watch for this eye tube to basically close, and then when it's open, the opening of the wedge is the peak or the balance. So when the balance occurs, on both sides of the balance, the wedge shape will close. So in rotating this now, I'm not seeing any activity. Absolutely nothing, actually. So again, we know it's 3 microfarad. That really should be between the 2 and the 4 right there. So there is no activity happening whatsoever on the eye tube in this capacity test. So we know the eye tube functions because it was working just fine for the leakage test, but no response whatsoever on this test. So it does appear that there is a problem. Now, the 12A7 tube, let me zoom back out a little bit here. This 12A7 tube over here has 2 sections in it. It has a rectifier and a pentode. The pentode is used during this test, so it is possible that there's a problem with the tube. The leakage test does not use the pentode, but of course all tests on here require power, and that's provided by the rectifier section of this tube. So we know the rectifier is working. The pentode would be in question. The filaments, there's 2 filaments in this tube, and they're connected in series. So we know that both filaments must be functioning correctly, because if one was open, then neither one would function. And because the diode or the rectifier section works, we know that the filaments are certainly working okay. Now, this top connection on this little top cap is the grid of the pentode. In the bridge circuit, we should see a signal on this input to the grid, because this is acting as an amplifier, which is then driving the eye tube. So because we're getting no response right now, let's take a look at if there's any signal on this grid. If there's a signal on the grid and there's no activity over here, the tube could be a problem. There could also be something between the tube and this eye tube over here, but the first thing is to check out that grid. So let me get this repositioned, and we'll take a look with an oscilloscope on the grid connection and see if there is any signal there. Here's the schematic of the capacitor tester. You can see the 12A7 amplifier section, or the pentode section right here, and the 12A7 rectifier section down here. Now you can see there's 2 transformers in the tester. T1 is the main power transformer. It's also where the filaments receive their power off of these windings down here. This T2 is the input to the bridge circuit, which is basically creating a 60 hertz AC signal to the bridge. And that signal, which is a sine wave, should appear at the grid over here. And this grid connection right here is that cap on the top of the tube. So you can see on the output side of the bridge, it goes through a capacitor, we have a resistance to ground, and then the connection to the tube. So not too much going on between the bridge and this tube. So we want to look for a signal at the grid input on the tube. Now you can see on the plate circuit, it comes out, we have a capacitor, some switching arrangements, and then into the grid on the I-tube over here. The I-tube is a 6E5. Now, a simplified version of this bridge circuit right here is like this. So here's T2 right here, and T2, the output on this transformer, comes up to the bridge circuit here and here, which on the schematic is right here and right here. Now, the test capacitor, which of course is across the test jacks, on the schematic is shown right here. We have a plus and a minus. So that's on this part of the bridge circuit. Over here on the bridge, this is connected to ground. So on right here, we have this coming over to ground on this part of the bridge. R2 is that main dial adjustment that you turn. So that's a variable resistance. And you can see that over here. And then another resistance, R1, which is the power factor control or adjustment. So I've just drawn that as a fixed resistor over here for now. And this resistance and this capacitance right here, on the schematic we have this resistance and the capacitors here. Those are selected by the test switches that are selected during the test. And for simplicity, I've drawn it just as one capacitor because that's all that is selected at any one time. So they have 3 capacitors, but depending on the range of capacitance that you're checking, only one is selected. Same with the resistors. We have 4 resistors shown here, but only one at a time would be selected. So again, we have 1 resistor. So here's the basic bridge circuit. We have a reference to ground on this side, and this side goes to the grid of the 12A7 tube, which is this connection right here. Now, the bridge is said to be balanced when you have a 0 voltage condition between this point and this point. And ultimately, that's what the I-tube will be looking for through that amplifier circuit, and then which ultimately drives the I-tube. This voltage across the bridge will be imposed or applied to the grid on the 12A7, and that ultimately affects the output and then the I-tube and its reading and how open or closed the I is on the, or that wedge segment opening and closing. So again, we want to see a balance of 0 volts across this bridge, and we can actually measure that, and we'll do so from here, which is on the positive terminal, the positive test jack, and of course the ground connection. So chassis ground and the positive terminal on the test jack. When the bridge is balanced, we should see 0 volts, and when it's not balanced, meaning that this range on this dial is above or below the capacitance, you'll see a voltage across the bridge. And when this is right at the capacitance, then the bridge is balanced and we have no voltage. So we'll look at that condition as well. But to start with, I will reposition the camera and we'll take a look at the signal on the grid and see what we have there. Okay, I have the oscilloscope set up so that we can take a voltage measurement on the grid of the 12A7 tube. Now the 3 microfarad capacitor is still connected to the tester. You can see it connected to the test lead sitting back there. The tester is on the C2 range for the capacity. It's in the capacity mode and for electrolytic, so that everything is set up. So we'll take a look at the voltage on the grid, which is this top cap right here. So I've got the probe connected to that top cap, and the ground connection of the probe is on the chassis ground of the tester. So you can see on the oscilloscope, the scope right now has a vertical scale of 100 millivolts per division. And that's really looking mostly like noise right there. It doesn't look like much at all. And if I rotate this control, look at this, so that's passing through the 3 microfarad setting on the dial right now, and it's really having no effect whatsoever on that voltage. Yeah, that's really just, there's nothing there. There should be a very large difference as this passes through the point where the bridge is balanced, and then going to either side of that balance point. This should make a very, very noticeable difference. So nothing happening there. So let's take a look again at the positive terminal over here. between this positive terminal and ground. Okay, let's take a look at the positive terminal, and the connection will be between the positive and the chassis ground, and we can see there's definitely a voltage there. So let's change the scale. Go up a little bit like so. Yeah, we definitely have a signal there, so that's good to see. So this is looking across the bridge circuit from the ground connection to the positive side of the bridge. And that positive side then goes through that capacitor and then over to the grid. So we have no signal at the grid, but we definitely have a signal coming out of the bridge. So we need to look at the capacitor and see if there's an issue with that capacitor. If I rotate the bridge, let's get a connection here on that probe. So you can see what happens when this is below this is a 3 microfarad capacitor, so this is below the 3 microfarad in its range, and you can see we have a very large voltage, and we come up through the 3 microfarad and then increase to the other side, and it begins to increase in voltage again. So that point right there where the waveform drops down, basically falls to 0, that's where the bridge is balanced. And just roughly looking where that stopped right there and fell to about 0 volts, yeah, that's a very good thing to see, because right here, this line on the scale is right on 3 microfarads. So it appears this is definitely trying to work. There's just an issue with getting that voltage over to the grid, because this is 0.2, 2, and then 4 right there. So right on the scale, right at 3 right there, that's where the bridge fell to 0 volts and became balanced. So, and if we go over here to the scale, I'll put it on 1 volt per division. You can see it's very sensitive there. That's a good thing to see. Right there, you can see the waveform goes from higher amount to a low amount and then increases again. And see, if you watch, I'm increasing the dial and continuing to increase it, but that waveform hits that basically that 0 point. So the bridge is definitely working, and the components around the bridge circuit are all functioning very well, because that waveform looks really good and it's responding the way that it should. Right there, when you really hit that point that it falls to about as low as it's going to go, it's exactly on 3 microfarads. So that's really good. That's really good to see. So let me get this repositioned, and we will take a look at that capacitor, and let me locate it where it is in this unit. I'm not sure. It must be, I would assume, near this wire that attaches to the grid. So we'll take a look in this corner over here and see what's going on with that capacitor, and if we need to replace it or what the issue is. So let me get this repositioned, and we'll take a look. Okay, I have the tester positioned on its side so that we can remove the 12A7 tube. The capacitor that we need to look at is likely located in this corner. The wire comes off of the grid cap and goes to a terminal board, and that capacitor is probably near that board. So I'll just remove this connector on the top. Comes off like so. And then to remove the tube, just walk the tube around in the base and lift up. Has some resistance in the socket, like that. This is the UX7 type of tube, where it has 2 larger pins to locate when you install it. So those 2 pins allow it to only fit one way into the socket. They're actually the heater, or the filament, is across those pins. The I-tube is a UX6. It has 6 pins on the base. So with that out of there, and I think I can see the problem. So let me zoom in. So this capacitor is not connected to anything right here. On one side, it seems very loose in here too. So there's our trouble. That capacitor should be connected to this terminal board right here, and it's just sitting in there loose. So that's why we have no signal on the grid of that tube. So I will get a new capacitor installed, and let's take a look at what the value is of that. Let me zoom the camera back out. So again, in that circuit, that was C5, and capacitor C5 is a 0.05 microfarad, 400 volt. So in a modern capacitor would be a 0.047 microfarad. So let me get that capacitor installed and I'll be back. Okay, I have the capacitor installed. You can see it down here. It's a 630 volt rated capacitor. The old capacitor was rated at 400 volts. As often the case with the modern new capacitors, they're physically smaller than the old capacitors, even though they have a higher voltage rating. So I'll get the 12A7 vacuum tube reinstalled, and then we can try out the capacitor tester, see how well it functions. So here's that 12A7 tube. And you can see on the right side, you can see the rectifier section, and in the center, the cylindrical section is the pentode. And the shiny area down here on the side, sort of comes around here, is known as the getter. Most vacuum tubes have a getter inside of them. And the purpose of that is to absorb impurities throughout the service life of the tube. So the getter is flashed during the manufacture of the tube after a high vacuum is pulled inside the tube, and there's a high RF or a strong RF field applied around the tube, and the getter is flashed and adheres to the wall of the tube. And the getter absorbs any impurities that are released during the normal operation of the tube to keep that pure, perfect vacuum inside the tube. So tubes that are aging and reaching the end of their service life often have a getter that begins to turn sort of a chocolate brown color, and it loses this shiny metallic color that the getter has when it's new. So we'll install the vacuum tube. Those two pins that are larger go to the front section right here, so that only installs one direction in the socket. Walk the tube around a little bit there, it seats right in. Put this top connector on the cap, and we'll get the tester repositioned and ready to check out. Okay, I have the capacitor analyzer set up for the capacity test, and we'll see if our replaced capacitor in that grid circuit solved the problem. Now over here on the test leads, I have a 3 microfarad capacitor attached. It's a known good capacitor, so if the tester is functioning correctly, this dial should indicate at 3 microfarads. So we'll want to watch the eye tube up here. The leakage label up here no longer applies because the eye tube will be opening and closing as we rotate this control, and that will show the balance on that bridge circuit. So when the eye is completely open at a maximum opening, that's when the reading is taken for the value of the capacitor. So over here on the switches, we have the leakage capacity test in the out, so it's in capacity. Electrolytic, this is in the in position, and this is in the in position for the sensitivity control, which is this control down here. So watching the eye tube over here, you can see it's closed right now, it's a solid green. I'll begin to slowly increase this up. And you can see the eye is now starting to open. So that's a good sign. And now the eye is closing again, so any further movement, the eye remains closed. So we want to back up, turn the dial back down to the point when that eye reaches a maximum opening. Right in there. Now you can use the sensitivity control to really zero in on that, and if you turn the sensitivity up, the eye closes and it becomes more sensitive, and you can watch for the slightest change. It's very sensitive when you move this. As you can see there, the eye is completely closed. So right there is about a maximum opening. I turn the sensitivity down, you can see it opens up very wide there. Turn the sensitivity back up again. Eye basically closes all the way, and then any slight movement here will basically right there. I'll zoom the camera in. I'll do this a second time just looking at the eye tube. It may be a little bit hard to see on the camera right now. But really that looks like the maximum point right there where the eye is open as wide as it will go. So taking a reading right here on the dial looks very, very good, because on the C2 scale, so it starts at 0.2, then it goes to 2, and then to 4. So 3 microfarads is right in the middle, and the indicator line is right on the 3 microfarad, and then it's just slightly below it, just ever so slightly below the 3. And that's perfectly acceptable. That capacitor has a tolerance, plus minus around the 3 microfarads. So very, very good that the tester is reading that precise and that accurate. So at this point, the tester appears to be functioning correctly in both the leakage and capacity tests. So let me zoom in one more time and do the test again, and I'll just zoom in closer on the eye tube so that you can see how that looks. So with the camera zoomed in, let me do the test. I'm going to shield this from the light overhead here. I have most of the lights turned off, but there's just a lot of glare on that tube. There we go, like that. Okay, so I'm increasing the control. You can see the tube is indicating, the eye is indicating a wider opening. And then as I'm still increasing the control, and you can see the eye is now closing. So I'll back up. Now I'm lowering the control back down, looking for that maximum opening right there. Really appears to be the maximum that the eye will open. And again, looking at the setting of the control, just swing the camera over here. You can see we're on the second scale in, because it's on the C2 scale. So C1, C2, 3, 4, 5, and 6 going in. So C2, we have 0.2, then 2, 3, and then 4, and you can see this line is right on the 3 microfarad. So very, very accurate. The tester is certainly functioning correctly at this point, and in both the leakage and the capacity tests. So at this point, the Cornell-Dubilier BF-50 capacitor analyzer is functioning very well, even though it has many of the original capacitors still in the circuit, and some of those capacitors could electrically be leaky or drifted in tolerance some. The old wax capacitors, it's not uncommon to see that, particularly with capacitors that are of the age that would be in this unit. So again, it's functioning very well given that we replaced just 3 capacitors. But we know that the main components like the transformers, the tubes, the various controls, switches are all working very well. And as a future restoration project, I will go through and replace the remainder of those capacitors, and it'll get this tester working really the way it left the factory, and it'll be reliable and something that can be used on the bench for troubleshooting on future projects. So if you enjoyed this video, give a thumbs up. And if you haven't subscribed to this channel, now would be a good time to do so. So until next time, goodbye.